Hey there, science fans. Welcome to another exciting episode where we unravel the mysteries of the universe. Bill Nye here, and today we're diving into the fascinating world of fiber optic cables. These slender strands of technology have transformed our world in ways you might not even realize. These amazing cables have revolutionized the way we communicate. From the internet to phone calls and even television, fiber optics are at the heart of it all. They use light to transmit information, which makes them incredibly fast and efficient. Imagine sending data at the speed of light. That's the magic of fiber optics. Imagine you could send a message at the speed of light. This isn't just science fiction, it's the reality of our modern communication systems. That's what fiber optic cables do. They convert electrical signals into light, which then travels through the cables to its destination. They carry data in the form of light pulses, allowing for lightning-fast internet, crystal-clear phone calls, and high-definition video streaming. Whether you're watching your favorite show or video chatting with a friend across the globe, fiber optics make it possible. These cables are like tiny pipelines for light. Inside, they have a core that carries the light and a cladding that keeps the light from escaping. They're made of thin strands of glass or plastic called optical fibers. These fibers are incredibly delicate yet remarkably strong, capable of bending and flexing without breaking. Each fiber is thinner than a human hair, but don't let their size fool you. They're incredibly powerful. Despite their minuscule size, they can carry vast amounts of data over long distances without losing quality. Fiber optic cables are essential for our modern world. They form the backbone of our global communication networks, connecting cities, countries, and continents. They connect us globally and power countless technologies we rely on every day. From streaming services to online gaming and even remote work, fiber optics are the unsung heroes behind the scenes. So buckle up, because we're about to explore the science behind these amazing cables. We'll delve into how they work, their history, and the incredible innovations that have made them a cornerstone of modern technology. Stay tuned and let's light up the world of fiber optics together. Now let's talk about the two main types of fiber optic cables, single mode and multi-mode. These two types are fundamental to understanding how data travels through the vast networks that connect our world. Whether it's the internet, cable television, or even telephone lines, fiber optics play a crucial role. The difference lies in how they transmit light. This distinction is not just a technical detail, it has significant implications for the performance and application of the cables. Single-mode fiber has a very small core, about 9 micrometers in diameter. That's super tiny. To put it in perspective, it's about 1/10 the thickness of a human hair. This tiny core is designed to carry light directly down the fiber with minimal dispersion. This small core allows only one light path or mode to travel through it. This single path minimizes the chances of light bouncing around inside the core, which can cause signal loss and degradation. Think of it like a single-lane highway for light. On this highway, there's no traffic congestion, and the light can travel long distances without much interference. Multi-mode fiber, on the other hand, has a much larger core, typically 50 or 62.5 micrometers. This larger core is more accommodating, allowing multiple light paths to travel through it simultaneously. This larger core allows multiple light paths to travel at different angles. These multiple paths can lead to more data being transmitted at once, but they can also cause more signal loss over longer distances. Imagine a multi-lane highway for light. While it can handle more traffic, the chances of collisions and slowdowns increase, especially over longer distances. So which one is better? The answer isn't straightforward. It really depends on the specific needs of your network and the distances over which you need to transmit data. Well, it depends on what you need it for. Different applications require different types of fiber optic cables, and understanding these needs is crucial for making the right choice. Single-mode fiber is best for long-distance transmissions, like connecting cities and countries. Its ability to carry light over vast distances with minimal signal loss makes it ideal for these applications. It can carry data farther without losing signal strength. This makes it perfect for telecommunications, internet backbones, and other applications where data needs to travel long distances reliably. Multimode fiber is great for shorter distances, like within a building or campus. Its ability to handle multiple light paths makes it suitable for environments where data needs to be transmitted quickly, but not necessarily over long distances. For example, in data centers, multimode fiber is often used to connect servers and other equipment. The shorter distances and high data rates make it an excellent choice for these environments. In summary, both single-mode and multi-mode fibers have their unique advantages and are suited for different applications. Understanding these differences can help you make informed decisions about your network infrastructure. As our world becomes increasingly connected, the role of fiber optics will only continue to grow, whether it's for long-distance communication or high-speed data transfer within a building. Choosing the right type of fiber optic cable is essential for ensuring efficient and reliable connectivity. So next time you think about the internet or any other form of digital communication, remember the tiny fibers that make it all possible. They are the backbone of our connected world, silently and efficiently transmitting the data that powers our lives. Now you might be wondering what's with the NM after those numbers. It's a common question, especially if you're new to the world of fiber optics. Well, it stands for nanometers, which measures the wavelength of light used in the fiber. In simpler terms, it's a unit of measurement that helps us understand how light travels through these tiny cables. Two common wavelengths used in fiber optics are 850 nanometers and 1300 nanometers. These specific wavelengths are chosen because they offer unique advantages for different types of data transmission. 850 nanometers is like the short-distance runner of the fiber optic world. It's optimized for shorter distances, making it ideal for applications within a single building or a campus. It's great for transmitting data over short distances with high power. This means you get fast, reliable connections without much signal loss, which is crucial for high-speed internet and data transfer within confined spaces. Think of it as the sprinter of light. Just like a sprinter excels in short bursts of speed, 850 nanometer fiber excels in short-range, high-speed data transmission. On the other hand, 1300 nanometers is the long-distance runner. This wavelength is designed to cover much greater distances without significant signal degradation. It can travel much farther with less signal loss. This makes it perfect for connecting networks over long distances, such as between different buildings or even different cities. It's like the marathon runner of light. Just as a marathon runner can maintain a steady pace over long distances, 1300 nanometer fiber can carry data over long stretches with minimal loss. So, if you're setting up a network within a building, 850 nanometer multi-mode fiber might be a good choice. It's efficient, cost-effective, and perfect for short-range applications. But if you're connecting two cities, you'll need the long-distance capabilities of 1300 nanometer single-mode fiber. This type of fiber is designed to handle the demands of long-distance data transmission, ensuring that your connection remains strong and reliable over many miles. Understanding the difference between these two types of fiber is crucial for anyone involved in network setup and maintenance. It helps you choose the right type of fiber for your specific needs, ensuring optimal performance and efficiency. In summary, 850 nanometer fiber is your go-to for short, high-speed connections, while 1300 nanometer fiber is best for long-distance, reliable data transmission. Knowing when to use each type can make a significant difference in the performance of your network. So next time you see those numbers, you'll know exactly what they mean and how they impact your network's performance. Whether you're a short-range powerhouse or a long-distance runner, there's a fiber optic solution that's perfect for you. Section 4. How many fibers in a cable? More than meets the eye. You might be surprised to learn that a single fiber optic cable can contain hundreds or even thousands of individual fibers. It's like a bundle of light-carrying straws all in one protective jacket. The number of fibers in a cable can vary widely depending on its purpose. A small cable used for home internet might have just a few fibers, but a large cable used for undersea communication can have thousands. This high fiber count allows for massive amounts of data to be transmitted simultaneously. It's like having thousands of phone lines packed into one thin cable. Section 5. Decoding the fiber rainbow, identifying cables by sight. Believe it or not, you can often tell what type of fiber optic cable you're looking at just by its color. Yellow usually indicates single-mode fiber. Orange is typically used for multimode fiber optimized for 850 nanometers. Aqua is often used for multimode fiber optimized for 1300 nanometers. Of course, these are just general guidelines, and there can be exceptions. But it's a handy trick to quickly identify cables in the field. Besides color, you can also look at the connector type to get clues about the cable's purpose. We'll talk more about connectors in the next section.